Okay, good morning, everyone. Can you hear me? Yes, no? Can someone confirm? Can you hear me?
Sir.
Yes? Okay. All right, we have waited enough. Let's start. Others can join, but I see only 10 people today. Okay, let me share my screen. All right, let us start. Because it's just a 50-minute session, we cannot wait more. So anyway, you are going to have your exam tomorrow. So it will be a typical Google form and 30 marks. So most probably I'll be giving 20 simple 1 mark questions from whatever we had discussed till now, and maybe 2 5 mark small numerical problems. Okay, shouldn't be difficult if you go through whatever we had discussed till today. Anyway, let me pick up a particular slide that I wanted to show you. All right. I mentioned about nanotechnology being acceptable or not. Many people were frightened initially. Even now, people criticize. Some say, no, this is not good. It may be dangerous. Okay. So just to make the point clear, see, I don't know if you know about this place called Chernobyl in Russia, where there was a nuclear blast. It was like a huge nuclear reactor blasted. At the time, almost 4,000 people immediately died, and about 600,000 directly affected. And now it is a dead city. Only I think 1 or 2 or 3 people are in that area, because the whole city is dead now, because nobody, the radiations are still there. But has that sort of stopped us from exploring nuclear energy? So the thing is, unless we are careful with what we are doing, anything which is looks very good may become very dangerous. So, but I don't think nano can go to that level of dangerousness, and we need to accept it. So this one I again put in. That is what we feel that it is a environment friendly technology. Okay. So these are some of the questions put up by Sir Richard Feynman. I told you about that famous lecture he gave in 1959 during his Nobel Prize. So he was asking, why can't we manipulate material atom by atom? Why can't we? Well, at that time it was impossible, and people couldn't accept it, and they had no answer. as to why we can't, but they know that we can't. But actually we can, and we are doing that now. Why can't we control the synthesis of individual molecules? Why can't we control how the atoms sit in a molecule? Okay. Why can't we write all of human knowledge on the head of a pin? That also I mentioned before that it is possible, and we are doing it now. Why can't we build machines to accomplish these things? So why can't we build these machines that can help us to do all these activities? Well, we have the machines now. I will gradually go to the discussion of the machines in the later classes. Okay, so these are some of the questions that were put up by Sir Richard Feynman. It will be important if you go through these for your exam. So I will share these slides with you today, and you just go through the slide contents also. Now, this is a very beautiful example of nano material being used long time back. Okay, I tell you, the nanomaterial has been used extensively long time back also, but people didn't know that they were working with nanomaterials. Okay, so this cup, I don't know if I've shown it before, but let me show you again. So this is a famous wine glass, or it's called a cup, the Lycurgus cup. Okay, Lycurgus is not the name of the king who had this cup, but it was the design of it. This is from mythology, Greek mythology. You see one king being pulled down by some veins inside the ground. Okay, that's the design on the cup, and that is King Lycurgus from mythology. He was pulled into the underworld by ambrosia using these veins. So if you look at it now, you are seeing it green, right? All of you are seeing it green. So when light is reflected from the cup, then the cup appears green. So at that time, it was like magic, where people used to go and see this cup. It belonged to a Roman emperor at AD 490. And if you let the light pass through, then it is reddish or purplish in color. Now this was magic at the time. We didn't know what happened or how it's happening, but now with technology, after the 1980s, people started studying the Lycurgus cup, and they found out that it is because of silver and gold nanoparticles embedded into the matrix of the or you can say of the silicon matrix. Okay, so it appears red in color. Okay, this is simply because of diffraction of light by these nanoparticles. Okay, and this is supposed to be one of the most beautiful example of the use of nanomaterials, that too thousands of years back. Then it was Michael Faraday who did some studies with nanoparticles, and he prepared gold nanoparticles. As you can see, he used to smear gold nanoparticles on a glass slide and did some optical studies. So you see the glass slide appears red, okay, because nanoparticles, gold nanoparticles at that size range is not golden. It can be anything between red and blue and black and all those. So the particles he made were about uh, you know 20 nanometers, and at that range it is reddish in color. Okay, so what you see here are some fluorescent nanoparticles. Okay, so when light falls, they are glowing, and this is of the same material again. Just by the variation of the size of the particles, the colors have changed. This I think we already discussed about the different types of nanoparticles based on the quantum confinement. That means the movement of the electrons in any of the three dimensions. Okay, so if you can restrict the movement, that means the size is so small that even the electrons cannot move. Okay, then we are talking about nanoparticles or quantum confinement. Now I'll continue with the problem we'd given before. I actually made a video yesterday and tried to send it to you guys, but I think the size became too big. I clicked it with my iPhone. I mean, recorded it on my iPhone. I don't know how to share. Maybe uh, let me try to see if I can share from my iPhone, because I've not been able to send you. Let me connect from my cell phone also. And let me see if I can share the screen. Then maybe I can put the video. But the thing is, you need to write down, I guess. I'm trying to solve two small problems for you. Okay, connected. I'm connected through the phone also. Okay, let me try to share this screen. How to do it? Share content. Mm, Can you guys see my phone screen? Yes?
Yes.
Okay, let me play the video. Can you see the video?
Yes, sir.
Let me play it. You tell me if you hear the audio also or not.
Evening, students. It appears that most of you have not yet understood the problem, right? The assignment.
You
I
can
only
hear
got
it?
one student who submitted, and he, of course, tried some mistake maybe. But what about the others? Uh, okay, so I thought maybe we'll look at it very simply, and hopefully you'll be able to understand this. So let me try to explain this in a very simple way. Let's take a very simple example first. Say, let's suppose we take a square substrate, right? And just to make life easy for us, we'll assume that this is 4 centimeter by 4 centimeter, and on this surface of 4 centimeter by 4 centimeter we want to put some balls, and the balls are spherical of suppose diameter 1 centimeter, big balls. All right, now if we want to put this size balls on this surface, how many of them can we put? Now you see the diameter is 1 centimeter, this is 4 centimeter, so naturally if we have to put them in here, so we'll have 1 2 3 4. My they are not same size, but as you can see these are all 1 centimeter, so 4 of them will sit here, and similarly another 4 will sit on this side. Okay, they're all same size. Okay, so ultimately if we just continue, what will happen? We will actually have 16 of these balls sitting here. All the balls are of diameter 1 centimeter. Now once we put these balls, let's see how much change in the surface area we are getting. Say, if I say surface area of the substrate, let's say S for substrate, this is equal to 4 into 4, right? That's 16 centimeter square, right? Now that is the base. Now on top of that we are putting these balls, and the balls will give some amount of surface area increase. So now what is the surface area of the ball? So it will be 4 pi r square. So that will be then 4 into 3.14 into r will be now 0.5 centimeters, right? Because diameter is 1 centimeter, so it is 0.5 square, right? So this should come out to be 0.5. 0.5 is 0.25 into 4 is 1. It's 5. So it should come out to be, I'll say 2 into 1.57 centimeters square. Okay, now why I'm saying 2 into, it can be directly multiply also, but then since we are only getting half of the surface area available for the ball, because if I want to show you as a three-dimensional figure, you'll see it's something like this, right? Say suppose these are the 4 balls on one side, then next balls will be here, that's 8, then 9, 10, 11 and 12, 13, 14, 15 and 16, right? So if you look at it effectively, actually half of these balls are like this, half of these balls are on the surface. So that's why we will say we'll take half of this, right? Therefore you can say surface area of the ball which is exposed will be half of the actual surface area. So we can remove these two, it will be 1.57 centimeter square. Okay, you do the calculation, you'll find it. It will be, you can use a calculator. So it will be, hope you understand this, right? We are taking half of the surface because only half will be exposed. Therefore, total surface area from all the balls, total surface area, if I write from the 16 balls, it will be 16 into 1.57 centimeter square, right? Now let's see the percentage increase. So what will be the percentage increase in surface area? So this will be the final surface area, that's 16 into 1.57 centimeter square by the original, that means the substrate that is 16 centimeter square into 100, right? That will give you the percentage. So 16 16 you can cancel that out, so it will be 157 percentage, or you can roughly say that the surface area has increased 1.57 times. Fine. Now see the situation here. To get this amount of increase in the surface area, effectively your substrate height has increased, because if it will look something like this now from the side. Okay, something like this. So this was originally a very flat surface. Now the surface area has increased by how much? 1 centimeter, correct? Because of the height of the balls. So effectively, by increasing the surface height of the sample by 1 centimeter, we have managed to increase the percentage surface area by 157%. All right, now let's go down to the nano level. This is like all we're in centimeters, right? Let me just remove this one. All right, let's try another thing now. Let's say we are going to the nano size now. Suppose you have a substrate of size 1 centimeter by 1 centimeter, and we want to coat it with some nanoparticles of, say, let's say diameter 10 nanometers. All right, now again let's do it the way we did before, where we put in one ball after another. Let's also put these balls now of this size. Okay, so it will go on like this and it will continue, right? We don't know how many, and finally it will come here. Same way we can continue this way and continue, and we come to the last one. So if we multiply this into this, we get the total number of balls sitting here. Now let's see how many balls will sit here. So you can say number of balls what do I say, number of balls, if I say per centimeter here, because it's 1 centimeter, right, will be how much? It will be 1 centimeter divided by 10 nanometer. Now, how much is a nanometer? It's 10 to the power of minus 7 centimeter. Okay, so it will be 1 centimeter divided by 10 into 10 to the power minus 7 centimeter. So it will be 1 by 10 to the power of minus 6. That means 10 to the power of 6 balls, right? Or nanoparticles. Let me correct this, not balls. I'm talking about nanoparticles now. Okay. So we will have 10 to the power of 6 nanoparticles on one side. So on one side, we have from here to here, this is 10 to the power of 6 nanoparticles. Similarly, the same, it is also 1 centimeter. So we'll have another 10 to the power of 6. Therefore, what you can say, total number of nanoparticles, this should be equal to 10 to the power of 6 into 10 to the power of 6, that's 10 to the power of 12 nanoparticles. Okay, that's correct, right? Now let's do the calculation on the increase in the surface area. So if I say surface area of the substrate, that's 1 into 1 equal to 1 centimeter square, right? Now surface area of a nanoparticle, that will be 4 pi r square, and we will say surface area of the nanoparticle effective, that means what will be the exposed one. So let me call it exposed or effective. That will be half of this, so it will be 2 pi r square, right? So that means 2 into 3.14 into how much will be r now? R will be 5 nanometers, right? Because the diameter is 10 nanometer, radius will be 5 nanometers. That means 5 into 10 to the power minus 7 centimeters, and that's square. So must you get there? Then 2 into 3.14 into 5 is 25 into 10 to the power minus 14 centimeter square. Is that okay? All right, so that should come out to be 3 25 25 50 50. So it should come out to be, I think, 157 into 10 to the power of minus 157 into 10 to the power minus 14 centimeter square. All right, now therefore we say percentage increase. Let's calculate that. Percentage increase will be final, that means 157 into 10 raised to the power of minus 14 centimeter square into how many nanoparticles? 10 to the power of 12 nanoparticles, right? Divided by, we have 1, all right, and we multiply that by 100 to get the percentage. All right, so obviously 1 is fine. 157 into 10 to the power of minus 2 into 100. So obviously this will go out, so we get 157 percentage, right? So if you remember the previous calculation also, we got 157 percentage. That means 1.57 times more. But the difference here is that the substrate thickness, previously we found it to be 1 centimeter. Here it will be just 10 nanometers, right? So that will, you won't even observe it, you won't see it. 10 nanometers is so small, right? So Simply by increasing the height of 10 nanometers using these nanoparticles, we had managed to get an increase in surface area of 157%. Okay, so the problem I gave you will be something similar. Now you have to think about it, but I really want to see you solve this one. So day after tomorrow we have an exam, right? So let's meet tomorrow for the class 9:15, right?
Okay, let me stop
And
here.
we'll continue further and we'll discuss about what.
Stop here. All right. All right, we are back to my desktop now. All right, let me again share the screen. Hope you got an idea of the problems. I'll try to upload on YouTube. I don't know, yesterday I couldn't do it somehow. It was not happening, but I'll try again today and share the link with you guys once I can do it. All right, now how much time we have? About 10 minutes. No, more than that. We started at 9:15. Okay, we have some time. All right, now let's look at a few more simple problems. I'll share these slides with you. Just try to understand this. How many carbon nanotubes? So carbon nanotubes are very small tube-like structures of carbon. Okay, saying 1 nanometer in diameter. So the nanotubes are 1 nanometer in diameter. So how many carbon nanotubes of 1 nanometer diameter can be tightly packed into a cylinder defined by a human hair? 100 micrometer in diameter. That means if you take your hair, one hair to be a cylinder, how many of these carbon nanotubes you can pack in, along the axis? Okay. Assume packing is done parallel to the long axis and that packing efficiency is not a concern. Okay, you press and force in, so tightly packed. Fine. Have you understood? That means how many such 1 nanometer diameter tubes can we put inside a 100 micrometer hair? All right, a cylinder that looks the size of a hair. Let's see if I have the answer. Yeah. So I solved this for you. The area of the cross section of a 100 micrometer diameter hair is, so if you look at the hair from the front, then it appears like a small tube. So the area of the cross section, okay, that means the flat part of the hair, if it is 100 micrometer, the area will be pi r square. Okay, so that is, if you calculate, it comes out to be 7.85 into 10 to the power 3 micrometer square. Okay, now if you do the same thing for a nanotube of diameter 1 nanometer, then you are getting 7.85 into 10 to the power of minus 1 nanometer square. The same calculation, pi r square. So then you simply see that how many, no, you simply divide the surface area of the big tube, like the hair-like tube, with the surface area of the nanotube surface. Okay, so the number of tubes that can be packed into this area is, and that's 7.85 in 10 to the power 3 micrometer square. Now you look at the units. All right, don't mess up with the units, they should be of the same. Here the units are different, so you have to make the necessary calculations for that. So you divide 7.85 in 10 to the power 3 micrometer square by 7.85 in 10 to the power minus 1 nanometer square, and what you end up with, a whopping 10 to the power 10 tubes, or about 10 billion tubes, these nano tubes you can put inside a hair of thickness 100 micrometers. Okay, so that gives you the idea of how much amount of surface area we can actually avail, right? So 10 to the power 10 tubes inside a human hair. All right, so this problem I'll give you. You go through the calculations, very simple. Okay, all right, going to the next one now. Okay, there's another simple problem. Assume that a cubic shaped transistor, okay, transistor that is shaped like a cube, that means all the sides, length, breadth and height are same. Okay, and we say the chip has the transistor has a volume of 10 nanometer cube, right? How many would fit into a 5 milliliter drop of water? So if you just drop 5 milliliter of water, that is the volume, how many such transistors of volume 10 nanometer cube would fit into that 5 milliliter drop of water? So if, you know, let me see. How can I, what is it? So it's a, if currently 1 billion transistors are fabricated every second, how much time in years is required to manufacture this number of transistors? Right? Think about that. It's the number. If you say, even if you are making 1 billion transistors per second, how much time is required to manufacture this number of transistors that will fit in 5 milliliter drop of water? 5 milliliter, is extremely small, right? A typical injection is 5 milliliter. Anyway, uh, all right, so that's the solution. Again, it's simply like the calculation of the volume of 5 milliliter is already given to you. Right, that's 5 centimeter cube, and divided by the volume of one transistor, that's 10 nanometer cube. Okay, that should be nanometer cube, not -3 nanometer cube. All right, so it comes up to a whopping 5 into 10 raised to the power of 20 transistors. That means in 5 milliliter of water, you can put in 5 raised to the power of 20 transistors. So you are saying if 1 billion transistors are made every second, billion is 10 to the power of 6, 10 to the power of 8, right? 10 to the power of 9, sorry, 10 to the power of 9. So it would make approximately 16,000 years to make these many transistors. Okay, so it is safe to assume that this number is greater than that of all the transistors ever made. All right, so you can imagine what size we are talking about. Right, it's extremely small. Right. All right, so these are two more problems you should look into. All right, now this is another third problem I want you to solve. Okay, don't be surprised if you see this problem in your exam with some variation in the numbers, of course. But here you are saying how many cubes, 1 nanometer on each side. So cubes have the same edges, right? Length, breadth, and height are the same. So if I say how many cubes, 1 nanometer on each side means 1 nanometer by 1 nanometer by 1 nanometer. How many of these cubes can be carved out of a cube parent? That means a bigger cube of 1 meter in each side. That means if I give you a cube of 1 meter by 1 meter by 1 meter, and you nicely cut it out into small cubes of 1 nanometer by 1 nanometer by 1 nanometer, how many of these cubes you can get, right? So that means cutting a 1 meter by 1 meter by 1 meter into small cubes of 1 nanometer by 1 nanometer by 1 nanometer, how many of these cubes will you get? Okay, that is the first part of the question. And the second part is find the collective surface area of the nanometer size cubes. Okay, if you talk about the original cube of 1 meter by 1 meter by 1 meter, the surface area of that will be available surface. There are 6 faces, right, in a cube, and one face will be 1 meter by 1 meter, that's 1 meter square, and there are 6 faces, so it's 6 meters square, right? So the original cube is 6 meter square surface area. Now if you cut it into 1 nanometer size and then you calculate on the surface area available for from all these small 1 nanometer size cubes, how much will it be? You can calculate it out again in meter square. Okay, keep the unit same. So this 6 meter square surface area, how much will it increase if we cut it into small cubes? Okay, that is the question. So this solution, I don't have it, and I'll take it from you. Okay, and there's another problem I solved. I'll just send you a snapshot. Hopefully from the video you understood how it's proceeding. So I'll send you the snapshot. Spend some time today in the evening or whenever you can find today solving out a few of these. Okay, and the other questions, I'll say maybe 21 mark questions, simple questions directly from the slides and the small handout I gave you to study. So let's go through that, and you'll be able to answer them if you go through that. It's not very difficult. Okay, I'll keep the answers questions very simple, but I'll have two small problems like this, 5 marks, 5 marks, that you have to solve. Okay, So we'll have this test tomorrow during the class itself, right, from 9:15. Is it okay? I'll share the link, Google form link, and you can solve it in maybe, I think we can give you 1 hour, no problem. All right, for the 30 marks, right? And anything, any doubts you have on the slides that I'll share now, and also the problems, I'm around the whole day today. I mean till midnight. You can post in your question in the group, all right, the WhatsApp group, and if not instantly, you'll definitely get the answer back before midnight. Okay, so let me switch off my slides. So these are the same few slides I will share that for tomorrow. Okay, and we will pick up a new module, a new section next week, right? So anything you want to say? Any doubts? We have a few minutes till we finish off. Anything you want to say? But look at your attendance, okay? Because I took a snapshot today, so I'll be very particular. I don't want anybody not attending the class to give the attendance. You should be honest there. So only those who are attending gets the attendance, right? Otherwise, it's not correct. Fine. So let me stop the sharing. All right, so I could see at one time 18 of you guys. Now I see only 10 of you. Just hope it is sorry, internet. But unless you guys attend, you won't learn, okay? And there's no point in taking a course if you don't get to learn something. And I assure you, I'll try to not make it too boring. But then the enthusiasm should be there from you guys. But nice to see a few names are constant. At least a few of you are interested, I guess. So there's a lot more to learn. We will learn a lot, and hopefully we will be on campus. I don't know, but if we are on campus during this semester again, I'll be happy to take you to the lab and show you a little bit of how we make these nanoparticles. Okay, a little bit, maybe 1 or 2 days, I'll teach you how to make these nanoparticles, different types of nanoparticles. Okay, so fine, then let's stop here today. And any questions you have, please post on the WhatsApp group. And you try out the problems, the small problems I gave you. The original one, please solve that. And I would have loved to, what I'll do is for the first assignment I gave you, I'll also do the solution, but I'll not share with you. I'll just give you the tentative answer. I mean, if it might not be exactly same for all of you, but at least the range should be same, you know. That means the unit that you are choosing should be same, and then it will be acceptable. All right, so try it out, please, and let's meet tomorrow for the exam. Okay, so all the best to you guys. Meet you tomorrow. Fine, and ensure that everybody is present tomorrow, because I don't think we'll get another chance later. Okay, all right then. Thanks everyone.
Thank you, sir.